Just as a reminder, want to remind you of these two key concepts to always keep in mind that a lot of the adaptations we see are centered around maintenance of turgor pressure in living cells, and that water moves from less negative to more negative water potential. I want to show you a couple of scenarios that show the interaction of the different components of water potential. What we have here is a diagram showing an interface between a tracheid in a needle. So this is essentially like a leaf vein in a needle where that tracheid interfaces with a living mesophyll cell. So of course that tracheid is dead, the mesophyll cell is living. So keep in mind that water potential is the sum of osmotic, pressure, and gravitational components. We're going to ignore the gravitational components for this discussion. So we're looking at osmotic and pressure potential in these situations. So in this cell, this is a living mesophyll cell. So remember, living cells have a positive value for pressure potential. Okay, so that value of pressure potential is positive 0.3 megapascals. Now, living cells have a lot of solutes in their cytoplasm, so they have a negative value of osmotic potential. So in this case, the osmotic potential of this cell is minus 1.9 megapascals. Now, as a note, the value of the osmotic potential can be adjusted within limits. So the plant can load more solutes into the cytoplasm, often from the vacuole, and when that happens, that makes the osmotic potential more negative. That adjustment is called osmotic adjustment, which makes sense. What that does is allows that living cell to continue taking up water from the xylem, even as water potential in the xylem becomes more negative. But that's getting a little bit ahead. So I want to then look here. So the sum of the pressure potential and the osmotic potential is positive 0.3 plus negative 1.9. So that's negative 1.6 megapascal. So that's the total water potential of that cell. Now let's look at the situation in the xylem. So we've got this tracheid, which is right there, essentially attached to the mesophyll cell. And remember, in dead cells like tracheids, or in tracheids where water transport is occurring, pressure potential is negative. So the pressure potential in this tracheid is negative 1.5 megapascals. The osmotic potential here is 0. Now, there are some solutes dissolved in xylem sap. Remember, nutrients are transported in the xylem sap, but they're generally pretty dilute, and often so dilute that they have no appreciable effect on osmotic potential. So in this case, the osmotic potential of the xylem is 0. So the total water potential of that tracheid is the sum of those two, which is negative 1.5 megapascals. So what we can see then is in this situation, there's a water potential gradient from the tracheid into the live mesophyll cell. In other words, that second concept that I talked about, water moves from less negative to more negative water potential. So water will tend to flow into that mesophyll cell because of that water potential gradient. Now let's imagine a situation where water continues to flow into that mesophyll cell. And think about my model of a plant cell, of a water balloon inside a cardboard box. As water flows into that cell, the water balloon is going to swell up some more. What that's going to do is increase the pressure potential. So let's say as water continues to flow into that mesophyll cell, let's say water influx causes psi p to increase to 0.4 megapascals. So when that happens, then that causes psi water to become 0.4 plus negative 1.9 be negative 1.5. What happens then at that point? At that point, there is no gradient between the living cell and the xylem, and water uptake stops. And basically that mesophyll cell is in equilibrium with the xylem cell. So let's imagine then that water potential continues dropping in the tracheid. Let's say water potential, we have this situation where the living cell is minus 1.5. If water potential in tracheid drops to minus 1.6, at that point water will flow from the mesophyll cell into the xylem. That can actually happen. So if that happened, pressure potential would begin declining because the cell's losing water, and it might reach an equilibrium at minus 1.6 megapascals again. But if water potential in the tracheid continues dropping, that's a situation where osmotic adjustment might need to happen so that that mesophyll cell can continue taking up water. And that's what's happened in this scenario. So in this scenario, basically the soil's been drying out and water potential in the tracheid has become more negative. This is essentially a measure of water stress, is one way to think about that water potential. So water potential in the xylem, in the tracheid, is minus 2.2 megapascals. And this living cell has basically osmotically adjusted down to an osmotic potential of minus 2.5 megapascals. Still has a positive turgor pressure of 0.3 megapascals, so its total water potential is minus 2.2. So we're looking at this combination of cells at a point when they are in equilibrium. Basically, the water potential gradient is zero. These cells are in equilibrium and there's no net movement of water in any direction. So a further decrease in pressure potential in the tracheid will result in water loss from the mesophyll cell to the tracheid and a reduction in pressure potential. So if that continues happening, if psi p reaches zero in that living cell, it will plasmolyze and die. So essentially there need to be mechanisms then for preventing water potential in that tracheid from becoming more negative to the point where a negative gradient is set up and that cell continues losing water to the xylem beyond the point where it can osmotically adjust. And the short answer is basically stomatal closure is really the mechanism the plant has to limit further decreases in Psi-P and the xylem. We will talk about that in a lot of detail in subsequent lectures, but that's the short answer. So when I talked about the evolution of water relations responses centering around maintaining turgor pressure in living cells, that's sort of what I'm talking about. At some point when, for instance, the cells have reached their limit of osmotic adjustment, evolution has essentially programmed the trees to close their stomata at a water potential where that can become damaging and cells can die, for instance. Now, as turgor pressure approaches zero, think about that balloon pressing out against the cell wall. As those cells start drying, that turgor pressure becomes less, and that mechanical support associated with turgor pressure starts going away. So what that means, so when we see a wilted plant, really what we're looking at is just a plant which has pressure potential or turgor pressure in its living cells approaching zero. So this plant, this wilted house plant here, has been in the situation that we saw on the previous slide, and the xylem water potential has become more negative. The living cells have been losing water to the xylem, and that has been causing their turgor pressure to decline. As turgor pressure declines, those leaves lose that mechanical support from that turgor pressure and wilt. So when we see a wilted plant, that's sort of the last step before plasmolysis. Those living cells are on the edge, they're losing turgor pressure, and if they get much drier, they'll die. And so that's why wilting is an important, sign of water stress. But we look at this video and the guy adds water to that plant. When you add water, what do? Soil water potential becomes less negative. Water flows from soil to roots to leaves down that water potential gradient. The living cells take up water, and Psi-P in the living cells increases. And the plant unwilts. I don't know if that is even a word, but we'll see that when I play the video. Water potential in action. In this part, I want to talk about the concept of negative pressure. This idea is one of the weirder aspects of water relations. The fact that in actively transpiring vascular plants, water exists at pressures below the vapor pressure of water. So let me elaborate on that a little bit. What I'm showing here is a number line showing a range of pressures. So going along here, basically atmospheric pressure that we exist at here at sea level, atmospheric pressure is positive 0.1 megapascals. If you look at the older literature, basically that's 1 bar. So 1 bar is atmospheric pressure. The vapor pressure of water is positive 0.0023 megapascals. What that means is that this is the pressure below which liquid water becomes a gas. In other words, if liquid water is in a vessel and its pressure is lowered below positive 0.0023 megapascals, it will boil. So I'm going to show you an example of that. So what you can see is that this demo on YouTube,
once I drive out all the gas molecules,
sealed pressure chamber,
there'll be less molecules to collide with the surface, less force pushing down the surface,
see the water's about
and I should achieve a maximum rate of evaporation called boiling. So you can actually see it starting to happen now, and there's our boiling.
Water starts to boil. That's
now, I want you to take careful.
Due to lowering the pressure in that vessel below 0.0023 megapascals. So when the pressure gets below the vessel pressure, that water transforms from a liquid to a gas. It boils. So at pressures below this level, water, liquid water, should boil. But it doesn't. Okay, we know that, for instance, the water potential of moist soils about negative 0.05. We know that a transpiring temperate tree might have a water potential of magnitude about -2 megapascals, and some desert plants can have water potentials down to maybe -5 megapascals. Not only are those water potentials, and one way to think about this is psi p in the xylem. So that's the pressure potential in the xylem. Not only is it below the vapor pressure of water, it's negative, so it's very much below. So this is really an unusual situation in nature. Xylem is probably one of the few places in nature where water exists in a liquid state below its vapor pressure. So what that means, we know the water in xylem is liquid, so liquid water in xylem exists in a metastable state. In other words, Due to its pressure, it should be gas, but it's not. It's liquid. And there's a couple of reasons for that. So how? How is water maintained in that metastable state? Well, first, there are no air bubbles in the water. Okay, usually for a phase change to happen, there has to be a nucleating point. So, for instance, when you boil water on your stove, where do you first see the bubbles form? You first see the bubbles form along the bottom of the pan. That's where the phase change is occurring from liquid to vapor. And that's happening because there's little microscopic cracks in the metal of the pan, and there's actually an air-water interface in that crack, and that is nucleating the phase change at that point. In water in Xylem, that water is degassed, so there's no bubbles or dissolved gases in that water, so there's no nucleation points. That keeps that phase change from happening. In addition, there's adhesion of water to the cell walls, and that may also help stabilize the water column. But the main point is the lack of nucleating points for that phase change to happen. So that enables the water in Xylem to be maintained in a metastable liquid state at pressures far below the vapor pressure, the boiling point essentially of water. Now this existence of water at negative pressures periodically causes problems for the idea of cohesion tension, which basically, and I'll talk about cohesion tension in a minute, but in order for it to work, water has to exist at negative pressures in the xylems, and periodically that upsets people because especially physicists and chemists say, well, water can't exist below its vapor pressure in a liquid state, so there must be some other explanation for water transport in the xylem. And they invoke other mechanisms of water transport which don't require negative pressures in the xylem. Suffice it to say, over the years, the evidence continues to support cohesion tension and the existence of negative pressures in the xylem. But it is strange. It is a strange situation. It's actually, I think, one of the wonderful things about water relations in trees is the existence of these negative pressures. So just to sort of drive this home, let's think about a redwood tree. This is another great drawing by Robert Van Pelt of coast redwood. This one's 332 feet tall, so it's more than 100 meters tall. We know that water is pulled up this tree all the way to the top. And in order for that to happen, water potentials in the xylem have to be negative. But when we look at, for instance, the maximum suction pump lift, if you go into a pump catalog and buy a water pump that pulls water, they will list the maximum lift. And the maximum suction pump lift is 25 feet. So you cannot buy a suction pump that can pull water any more than 25 feet. Yet trees can pull water much greater distances. So, and that's because trees can maintain water at those negative water potentials. Whereas when a suction pump reaches that maximum lift against gravity, and I'll show you the math in a minute, at that point it's reached the vapor pressure of water, and that water will cavitate. It will boil. So if the maximum suction pump lift is 25 feet, how do we get water out of wells or pump it up hills higher than 25 feet? We push it. When we get water out of a deep well, the pump is at the bottom. For instance, if you live in a rural area and you have a well on your property and you've ever seen them repair the pump, they have to pull all the pipe out of the well, and the pump is attached to the bottom of the pipe and pushes the water up out of the well. Similarly, when water is transported in a municipal water system, it's not pulled by suction, it's pushed by pressure using pumps. So suction pumps have inherent limitations due to that fact that you can only generate a pressure difference enough between atmospheric and the vapor pressure of water. And I'll show you that math here on the next slide. So let's do the math for why a suction pump can only lift water about 25 feet. You're saying, why are we talking about suction pumps? Really, because essentially water transport in trees is by suction. It happens because there's a creation of a pressure difference in the xylem. So we can think of water movement in trees as essentially a big suction pump. But let's look at a man-made suction pump. That happens, let's say this is the pump, and this is a pipe. And that pipe is in the water here. That water at the pipe inlet is at a pressure of atmospheric pressure, 0.1 megapascals. This suction pump lifts water by creating a pressure difference. Okay? Lifts water by creating a pressure difference. Okay, so it lowers the pressure up here at the top. So that pressure difference causes water to flow towards the pump. So we can calculate what the maximum pressure difference is. So let's say the pressure up here at the pump is plus 0.05. That will allow water to flow up in that direction. But when the pressure in this pump reaches 0.0023 megapascals, at that point the water in the pipe will boil, because this is the vapor pressure of water. Okay, so what that means is that this is the biggest pressure difference that you can generate before water boils. So what is that pressure difference? So the pressure difference, so the maximum pressure difference equals that atmospheric pressure, 0.1 megapascals, minus that vapor pressure, which is basically the lowest that pump pressure can go before cavitation happens. So that difference, the biggest pressure difference then, when you subtract those two, is 0.0977 megapascals. Okay, so if you remember, the gravitational potential, basically to lift water, you need to generate 0.1 megapascals per 10 meters of height, or 0.01 megapascals per meter. So if we take that pressure difference, 0.0977 megapascals, and divide it by 0.01 megapascals per meter, okay, those megapascals cancel out. The units end up being meters, okay, and we end up with 9.77 meters. So a pressure difference of 0.0977 megapascals will enable you to lift water 9.77 meters. That's about 32 feet. Okay, no system is perfect, so probably the best man-made pump can only lift water about 25 feet. Okay, that's why. It's because that's the biggest pressure difference that can be generated before water cavitates is that much, and that lift is about 32 feet. In order to generate a bigger pulling force, a bigger pressure differences, the psi p in the water column has to go negative, and that's what happens in trees.